So today we actually dive more into the syntax, and the agenda for today is basically to get the basic compilation and running the program's process going, then go through chars, entry methods, and asynchrony, and illustrate those through some examples, and syntax, of course, for all of that. And then the idea of .ci file, the idea of a main char. I'm just enumerating them more to myself rather than to you, but those are the concepts, main chars, and maybe towards the end we'll do a little bit of read-only variables and parameter marshalling issues. Next lecture we'll start talking about collections of chars called char arrays in Cham++. And really, the one lecture after that, if I have my plan working right, then in that lecture you will learn basics of load balancing, basics of fault tolerance, how to make your program fault tolerant and dynamically balanced, and you are ready to write a full-fledged Cham++ program right after 3 lectures. But there is still a lot more to learn after that, but you will be able to do pretty sophisticated programs at that point in time. Okay. I need to figure out how to get rid of this. Maybe it's useful today. Let's see. So I flashed this particular. I'm going to just check for myself that this is working okay. In the back, do you hear it through actually any speaker? Okay. All right. So a Cham program is written, and we're going to look at the Hello World program in at least a C++ file, maybe a .h file, and then in addition you have to write this Charm interface file, CI file. And the CI file has its own syntax. Everything else is just regular C++. The CI file has its own syntax and probably somewhat finicky compiler. If you notice, and we have been trying to improve the language, the CI language, but whatever syntax it supports is very simple. But because it's very simple, the parser is also very simple. It's not very forgiving, or was not very forgiving of syntactic errors. In the last year, we have made some effort to make that part of it better. But so if you find any scope for improvement, say, in this situation I spent half an hour debugging this silly syntax, and if only the compiler had told me something. If you find issues like that, please report them on Piazza. We might make a separate place for it so that all those gets addressed as time goes on. That's how Cham++ has grown as users use it and tell us about what's wrong with it. But what happens is, once you start getting used to Cham++, those initial annoyances about .ci and so on fade away, because you have understood the finickiness of the compiler, right? And you don't see it anymore. You say, well, if I miss a semicolon, it gives me this weird error that I never can figure out after spending half an hour. I say, oh, that was a semicolon. And once you do that mistake 2 or 3 times, you won't make that mistake again. And you will not ask and you will not complain about it, because you know how to fix it. And therefore, it will never get fixed in the system. You see what I'm saying? So please, anytime you find scope for improvement, let us know. All right. So you have to write this .ci file. What is inside the .ci file? Basically, these are declarations of parallel aspects of your Cham++ program, right? And so those would be, we'll go through them hierarchically. In this particular program, you see a main module called hello, which contains a main char called main, and it contains an entry method called main. Of course, it's the same name. That means it's the constructor entry method, and its parameter is ck_argMessage star, a pointer to ck_argMessage. We'll explain all those components further. Then the .c program that goes with this for this Hello World program is this. In the .cpp file, you say include stdio.h, your normal C++ stuff. But notice those two includes. Include hello.decal.h at the top and hello.def.h at the bottom. Okay. So decal.h is basically contains declarations of classes generated by the system when it uses by using the information from the .ci file, and def are the definitions that it generates for those classes. So system generated information is kept in these files, and you must include it. Now, if you have a .h file, you will put this first statement inside at the top of the .h file, and this contains only definition, so it should be in C++ file. That's a more natural place for it. Okay. Now, what happens to the program? Your normal C++ program, you would write a header file and you would write a C++, CPP or uppercase C extension file. When you write a Charm++ program, you write those, the .h and .cpp, your usual files, but in addition you write the interface files. Okay, we saw that. And then what do you do? Well, then to compile, you provide the hello.ci file first to CharmC. Instead of using your C compiler, instead of saying GCC or CC or something like that, you say CharmC. It understands where some libraries are. Of course, CharmC is specifically for hello.ci. It has its own parser, so it will call that parser, right? But also for so now that .ci file has been parsed. It has produced those classes. They are included in your .h and .c files. Now you compile your hello.c file, producing the hello.o, and again you use CharmC rather than GCC. And this time it is because, you don't have to know why, but you should always use CharmC. For the link line, it is because of the libraries it is using. You don't have to type those names of the libraries and search for them. All of that is included here. Here also there are some things that it will know that you don't have to type. You could, in fact, look at what the CharmC script is doing and try to do it all by yourself in your makefile, but it's unnecessary. So you just use CharmC. And then to run the program, normally you would do something like charm run plus p7 hello. On top there will be a specific way of doing this with, for each machine, provides a way of allocating nodes and then running a program on that node. So we'll provide you what the specific instruction for Taub is. I think you already have seen that in this programming assignment. And the plus p7 command line parameter, the plus parameters are parameters that usually are consumed by charm run. That's like those are specified how many processes, how to start them up, how many, whatever. Variety of things. We are going to learn more of them later. So right now, let's just say plus p are meant for the system. You won't see them inside your program if you look at argc or argv. All right. So again, to emphasize, the .ci file ends up producing the decal and def file with what name? The name is the same as the name of the module. Okay. So if you say main module hello with a lowercase h, it is going to produce a hello.decal.h, hello.def.h. The fact that this was in hello.ci file doesn't make any difference. If you call this file pgm.ci and you compile it, it's still going to produce hello.decal.h and hello.def.h. It depends on what you put here, not what the name of the file is. Okay. All right. And so your declarations go here. .c file goes inside the C file. CharmC, which is a C++ compiler, basically produces the object file, which you link with other things and you run the program. So now let's get a little bit deeper into that syntax. So first construct we saw there was module. So a Charm++ program is organized as a collection of modules. So each module has one or more chars and char classes defined within it. And the module that contains main char, right now let's just say there is only one that contains the main char, is declared as the main module. Right? Later on we'll see, in fact, let me just tell you that it is possible to have more than one main char class and more than one main module as a result of that. The point of the main char is the program execution begins by creation of an instance of the main char. Again, we'll look at that when we look at the example. So each module will lead to, suppose you have a module, my module, then it will lead to my module decal.h, my module def.h. All right, so this I think we've seen module, my module, char definitions. If it is a main module, a module containing main char, then you say main module here. Okay. What is a char? Well, chars are, as we saw in the earlier lectures, chars are the parallel objects for chore, small task, that are managed by the runtime system. They have entry methods, and those entry methods are asynchronous. That is, you can invoke them and continue on. The invocation will happen at some point in future, and they can be invoked from objects running on different processors, different hosts, different nodes in the system. Okay, so look at this code here now. So there is a char, my char, and some entry method definitions, and then in the .c file, what goes corresponding to that is that there is a class called my char, right? And so you will say class my char. There is a char called my char, therefore you will say class my char. It has to be inheriting, it must inherit from this class. What is this class? Public cbase underscore and your class's name. Okay, so there is a base class for your class. Where does that come from? Anyone guess where is the definition of this class? In the decal.h file, right? We just generated using the .ci, the decal file was generated. That contains a declaration of each cbase class, right? And that will give you some inherited properties that are useful, as we'll see later. But you must always do this, and if you get some errors, sometimes you might want to just check, hey, did I inherit my class properly? All right. Next is the concept of entry methods. An entry method is again a C++ method, just regular C++, but it can be invoked remotely and asynchronously by another char. So in .ci file, inside this place where we said entry method definitions, you can put definitions that look like this. Entry my char, that is of course the constructor of the char my class my char. Entry void foo, entry void bar. Notice that of course the constructor has no return value. All the others have void return values. Why is that? Based on what we said about the language, there is a reason why those return values are void that you can guess or talk about. Anyone? Yeah? Right, they are asynchronously invoked. That means there is no return value coming to the caller char because it is the execution is going to happen sometime in future. So that void is indicative of the fact that you are not going to return anything, right? And so you can declare the parameters here. This has no parameter, this has no parameter, this has an int parameter. You can put any basic types you want for now. Later on we'll see non-basic types and how to deal with them, or even arrays. In the .c file, inside the class definition for mychar, you'd, or somewhere, depending on how you write your C++, you'd say mychar : mychar, write the constructor code. This is just your usual C++ code, mychar : foo, mychar bar int param. This and this must match. This is one of the sillinesses that we have to deal with because of the fact that Cham++ is mostly a library-based system, right? If it were a language which owns compiler for the whole thing, then you shouldn't have to duplicate this here and here. You would just declare it here and the system will understand what to do with it. But since we have to separate a .ci file so that you can create those generate those classes, etc., this declaration appears here as entry void bar. Of course, entry doesn't mean anything in C++. So in C++ it will just be mychar : bar. And the parameter here must be the same as this, otherwise the system is going to complain about mismatch, like some methods are not declared or not defined or something like that. And then you just write your usual C++ code here, right? So the execution, like I said, the whole program execution, when you say Cham run this program on 20 cores, it begins with constructor of the main char. The main char gets constructed, its constructor runs. On which processor or on how many processors? Just one processor, right? So the main char gets created someplace. Typically in implementations, it's processor number 0, but you don't really need to worry about it or know about it. But it will be constructed on one of the cores. And then the main char constructor takes a pointer to a system-defined class, which is ck_argMessage. All that you need to know right now for ck_argMessage is that it has two fields called called argc and argv, and then you know what to do with those fields, right? That's just a standard C++ argc and argv. So you know, if you have ck arg message m, where was our example program here? That m inside the public main constructor, if you want to print what's how many arguments you have, you will just say m arrow argc. That's the m, and m arrow argc will give you the number of arguments. M arrow argv will give the array of arguments as usual. Okay. Now, of course, the whole execution after that point continues on only because the main char created some work. Typically, it will create some additional chars unless it's a hello world program, in which case it won't. But in typical execution, it will create other chars, and they will execute and they will generate messages for others. And then you saw what happens with that scheduler picture in the second lecture. And so execution will continue in that fashion. Now, so now how do you create a char? A char is a C++ object. So it is tempting to say new some C++ object class name, right? New mychar. We can't do that because new mychar has a previously defined sequential semantics in C++. It just creates in place a C++ object, gives you and returns a pointer to it, right? That's not what you want. You want it to be created somewhere. The runtime system should take responsibility for balancing the load and putting it on some other processor, scheduling that constructor at some point when its turn comes and all that stuff. So we cannot use the new call. Instead, we provide ck is a prefix that we use often in charm. Ck stands for charm kernel. So the runtime system calls are often prefixed with ck. Okay. And so ck new is the call that we provide, and since we are doing it anyways and we are generating all those classes ourselves, might as well make it a generated method of a class that we generate. And so basically, if I have a char called mychar, the way to construct a new instance of it will be to invoke the cknew method on a special class called cproxy_mychar. Remember, we already saw cbase_mychar. That was this guy here that we have to inherit from. Where was that? If I have a class called mychar, then it inherits from cbase_mychar. And here we are saying you have to have cproxy_mychar. That's another generated class. Call it cknew method and provide to it all the constructor arguments. That's how you will create a new char. And this tells the system, hey, this is a char of this type being constructed. Here are the parameters. Take those parameters, package them, use whatever you want to do, use in the runtime system, find the processor where it can take root. And so that's why this is called sometimes a seed for a char that's generated here, and send it to some processor, and there when its turn comes, it will construct that object, right? And so, but at this point right away, we need some return value so that we can communicate to it in future. And one way of doing that is you can just say store it in a variable called proxy, and what is the type of this proxy? Was the same as this cproxy_mychar proxy equals the same call that we had here, cknew arguments, right? So does that make sense? You can create a char that you can specify that a char be created at some time in future by calling the cknew method on the cproxy_ version of its class, generated class, and then it returns a cproxy_mychar proxy to which you can then, using which you can do method invocations on it in future, right? So here is an example of a hello world type example again, but this time we are creating chars. In the .ci file, you have a main, let's call it a main module because it contains a main char, and called main. It has, so main char has a keyword here, main char, that tells the system, hey, begin by creating an instance of this objects on some processor. And it has a main entry, a main method, ck_argMessage star m. That's as usual. You always call it ck_argMessage, which is a system defined type. But then now we have a second char class. again, don't forget the semicolon here, etc. But the second char class is not a main char. It's not automatically created. So we just say char. Its name is singleton, and it has the constructor method called, of course, singleton, and that's the entry method. You don't put void for constructor, just following the C++ convention. Now again, the standard includes hello-decal.h, hello-def.h here, and then class main has now a which is inherited from cbase_main, has a public method called main. All char methods are entry methods are public, and non-entry methods are private. Right? There may be some exceptions. We'll learn about them later on, but that's the basic idea. And then all that this main char does is just creates one instance of singleton char. It doesn't even store a proxy to it for itself because it's not going to talk to it right now in this example. So it just creates an instance of that char. The singleton char has a constructor. Again, singleton is declared as a subclass of cbase_singleton, and it simply prints out hello world and calls ckexit. There are two things to notice here in that char's constructor. One is, that look like a typo, ckout. Well, it's not. I told you ck is a prefix that we use in charm. Ckout is the stream that you use for printing to the output. This is somewhat dated. It's possible that we might have, we can live with cout now. But originally, when all the prints are coming from different processors, they have to be merged into a single stream to be shown to the user at the front end. And so that's why we use a special one called ckout. These days, machines themselves support cout correctly, so it may be okay there. But ckout is what you should use following the form right now. And then the second thing is ckexit, not exit. And I think we went over this logic last time, because basically we want to tell all the processors schedulers to terminate. You are not just calling, if you just say exit here, the singleton char, the process on which it is running, out of 100 cores, one of them will exit. But all the other 99 are sitting there waiting for something to happen, right? Did I explain this concept last time or not? No, right? So I'm remembering from earlier in the month tutorial, but this is probably a good time to repeat my joke. Some of you who attend my lectures often will get the same jokes again and again, but that's okay. So it's not really a joke. It's how many of you read Hitchhiker's Guide to Galaxy? Yeah, okay. All right, those of you who did not, I strongly recommend it. But anyways, it's a science fiction comedy, if you want to call it that. And it's a trilogy consisting of at least 4 books. So in one of those books, our protagonist or hero, I don't know what to call this guy, but anyway, he enters another universe. And there's all kinds of fun stories about what happens in that universe. But he enters another universe, and then he escapes from some bad guys chasing him, and he runs to the airport, and he finds that there is an spaceport, and he climbs a space ship and gets into it somehow. And he finds that everyone is asleep in their seats. All right, and then a few minutes later, a big commotion starts. The robotic air hostesses come out, and people are just very agitated when they wake up, and they start screaming and so on. And they say, don't worry, we are going to provide you some refreshments and then send you back to sleep while we wait for napkins to arrive from outside, or supplies of napkins. Say, no, please take off. And say, no, napkins are a requirement. We have to wait for the napkins. And say, there is nothing outside. All the civilization outside has died out. There is nothing left on this planet. And says, no, civilizations, they will arise, they will go down, they will arise at some point. Surely the new civilization that comes up, those people, whatever they are, life forms, they will eventually develop napkins, and they will supply the napkins to us, and then we'll take off. Okay, so and then they turn everybody off, and they all go back to their induced sleep. So if we don't call ckexit, all the other schedulers on all the other processors are saying, there will be a message sometime in the future. I'm going to sit here waiting for it. Okay? And they will never exit. Your program will hang. in parallel programs, hanging, of course, in sequential programs, infinite loops are one way in which they hang. In parallel programs, there are lots of ways to hang your program, okay? And so, so you have to be careful, and this would be one way. You don't call exit, you call CK exit, which tells the system, hey, look, tell everyone on every processor, all the schedulers to terminate. We are no longer executing. Even if your message queues are non-empty at that point, whatever is in your queue, ignore it and exit, right? And then it will do some termination actions. It might store some performance data and things like that, and then it will exit. Okay. What is this idea of a proxy? Well, the proxy class is the class through which we invoke methods on it, right? I mean, that's what we did here. No, we didn't do that here, but I said when I was giving you the example. So what is a proxy and how do you get it? A proxy is used for doing a method invocation on a char object. Asynchronous method invocation on the char objects. How do you get a proxy? When you create one, create a char to ck new, it will return to you a proxy object. Other than that, when you are inside a char running some method, constructor or whatever, you can also access a special variable called this proxy. So this proxy, the P is uppercase, is a variable that you inherit from your cbase underscore mychar class. Remember, a char always inherits from cbase underscore class name. Well, that's where you get one of the things you inherit is this proxy. And so you can get this proxy and say assign it to a variable, say x equals this proxy. And then when you are invoking some method, you can pass this your proxy to them so that they can invoke a method back in you, right? So this is one way in which you pass your proxy to someone else. One way in which you get hold of a proxy is someone sends it to you as a parameter. The other one is you created them, so you have a proxy to them, right? So if for example, in this example, in this the foobar2 method has a proxy as a parameter. So cproxy underscore main has been passed here. So this is just a variable name here. And so you can say main.foo, and it will send the invoke the method foo in the main object, right? Not the object that called it, because I could call someone, they could call someone else, and keep passing the proxy around. And you have the proxy. That means you essentially have a pointer, a global pointer to that char. So a proxy object is equivalent to a globally valid pointer or a reference to a char class, right? Okay, and we already explained the ck exit, so I will skip that. So here is another example. So this time main module is called my module. It has a main char called main, etc. The same constructor, and we have a char called simple, and that simple char has two parameters, an int and a double. So at least you know that it can take a double as a parameter. So far we just had int. Okay. Now what does it do? Well, we're going to make our simple char calculate area, right? We should have given it a better name, but okay, it's simple also. So we called it simple. So what is the main going to do? Well, notice again usuals, class main public cbase underscore main, and then the main constructor is going to say just print hello world, but then also it is going to call the ck new, create an instance of simple char, to which that constructor it is going to pass two parameters, 12, which may be a radius for a circle, and who knows, that guy doesn't know the value of pi, so you're going to calculate it and give it to it, okay? Just silly examples, but yes, so we provide to it the value of pi. And so in some other universe where value of pi is different, maybe we'll pass another value, but okay, you think about that universe. So all that this does is takes that pi, it takes the radius, and it says the area of a circle of radius x is yxx, pi r square, right? And then just prints that and calls ck exit. Why does it call ck exit? Because there is nothing, we decided there is nothing more to do in this program after printing that radius, right? Okay, so does this program make sense? Any questions on the syntax so far about anything? Okay, because soon I'm going to start asking you questions. So you better, if you have questions, this is a good time to ask. Yes? Good question. So when you write charm programs, you are not supposed to know anything about processors. You write programs independent of the number of processors. But processors exist underneath, and once in a while you might get curious, where is this char running? And so ckmype is a way of finding out the serial number of the core on which this statement is executing. Okay? And PE, we will come and talk about what is PE. PE stands for processing element. What is the serial numbering? How are they organized inside a process and nodes and so on. But if you're running on 100 nodes, each with 20 cores, you might have 2,000 PEs. They are numbered 0 to 1999. Right? So that's the serial number for a PE is globally unique and contiguous. Okay, any other questions? Okay, so a couple of points to know. These are asynchronous methods. This means a couple of different things. First, of course, there is no return value. But also, think about this. You have you created a proxy for a char called mychar, and you got a proxy on it, and you say proxy.foo, proxy.bar. You invoked two methods on that char right there. Right after you created it, you send two invocations to it. But those method invocations will go packetized. Remember what we said? Well, and then they'll be put inside an envelope and put in the mailing system, the network, and it will go to the right place where the char lives, and it will go in its scheduler's queue. Proxy.bar 5, take the 5, put it in the envelope, put all the destination object, etc., create that serialized packet, send it towards that processor. There is no guarantee that they will end up reaching that destination processor in the same order, and you might even have assigned priorities to it. We haven't going into that yet, but irrespective of that, there is no guarantee even in the baseline to say that foo will execute first on that object and then bar, even though the originator is the same object. Of course, if there are two different objects sending to a method invocation to another object, there is no guarantee because it's like a relativity, right? The notion of simultaneity doesn't exist in parallel programs. And so unless you impose it through synchronization, you cannot get synchronization. And there is always a cost for such synchronization, and we don't want to pay that cost unless we are willing to. Unless the program is willing to, and so the baseline default behavior in Charm++ is the execution can be out of order. And this is probably the single biggest initial hurdle other than the syntax that you have to overcome when writing Charm++ programs. You will see some really trivial example today like this one here and so on, and you'll say, come on, that's obvious. But when you're actually debugging your programs, you will need to come back to this idea because our mind likes to work sequentially. It likes to think this object does this, and then it does this, and then it does that. And it says, why do I say then? Is it because of some inherent ordering, or is it just my assumption that, oh, I sent it the foo first and then bar? Obviously, it will do foo first and then bar, right? So you have to free yourself of such assumptions and learn yourself to deal with asynchrony very carefully. So now another thing is that another policy or another semantic guarantee is that only one method of a char will execute at a time, which in practice means a char is anchored to one core, right? That's one way of satisfying that. So if foo is executing, the bar cannot simultaneously be executing on some other core, for example. Right? Does that make sense? So the parallelism is not inside a char. Parallelism is between chars. Right? Okay. So char is a unit of parallelism. It's a unit of decomposition and so on. Okay. Yes, and later on, all of these, initial lectures are going to contain a series of lies. And I'm going to go back on those lies later on as I introduce more sophisticated concept. But really, the baseline to understand it, just trust those lies. Okay, yes?
So within a char, we don't have to worry about synchronization.
Within a char, you never have to worry about a lock. You don't have to worry about yes, no synchronization is needed inside a char. That's actually a very useful property for writing efficient code. You get an encapsulation that's guaranteed to be atomic, that's guaranteed not to have any synchronization issues, race conditions. There will be race conditions between chars like this one. Foo comes first or bar comes first. That's a race, right? That level of race condition you have to deal with explicitly. But data races inside a char, no, there aren't any. Okay. Okay. So foo says foo executes and bar says bar executes with this parameter. Those two prints can occur in any order. Not just that, if you have the same method name, this is obvious, but let's re-emphasize it. You have a method name called bar, and so you are calling proxy.bar 7 and proxy.bar 5 from the same source object, in fact. They can be delivered in any order. Bar is going to just print bar executes with whatever parameters given to it. So the output can be bar executes with 5, bar executes with 7, bar executes with 7, bar executes with 5. The system guarantees a single CK out with an endl, doesn't get garbled. The two statements will not get interleaved and mixed like that. But other than that, they can occur in any order. That makes sense? Okay. Let's look at a variation of our example. My module and contains a main char called main. The simple char class contains not just the simple constructor which has the y as a parameter. Remember we sent pi last time there, but it also now has gained a new method, entry void find area. So instead of this guy doing it, we're going to reuse it many times and say find area of this radius, find area of that radius, and so on. And it has a Boolean parameter called done. Right? By the way, looking at a .ci file is very useful. You should try to make CI files as descriptive as you can, and later on when you learn some new construct, you can actually make more or less the structure of the parallel program becomes clear by looking at the .ci file. So oftentimes when I look at your project designs and so on, I would ask to look at your CI file and with some comments explain what it is doing. So use it in that fashion. Now here the main char is simply saying, let's create an instance of the simple char, of course by calling cproxy_simple, ck new, pass to it pi. Well, we're going to stick with that fiction of you need to pass the value of pi here. And then what does this return? It creates an object, it creates a char eventually, but you already have a proxy to it, right? And so cproxy_simple sim, you have a proxy. Now this object is going to be invoked by us many times. We're going to invoke it 10 times, right? I going from 1 to 10, that's 9 times. Sim.findArea I false. Basically, you are saying find and print, find the area of a circle of radius 1, print it, find the area of circle 2, print it, and so on. And then last one is sim.findArea 10. Remember, we didn't pass 10 here, it's less than 10. So sim.findArea 10, we're going to say true. What is the intention? What are we trying to do? What is the false parameter doing? That parameter is basically saying that's the last one. So the name of that parameter we used was done. So if you say false, that means I'm not done yet. There is more coming, right? And when you say true, that means, hey, that's the last one. You can call ck exit now, right? So when I say find area 10 true, what I'm trying to tell that object is print the area of a circle of radius 10, and then call ck exit. No more values are coming to you. And the simple class does this. Find area of circle is, remember when you got, this is a very common thing in Charm, constructor parameters get stored as class variables. This is just normal C++ idiom as well. And so we store the value of pi that came in as y, and so that you can print here yr square as the area of a circle of the radius that's given to you here. And then if this Boolean says done, so otherwise we just can go back. Otherwise, if it says done, we call ck exit. What if it is not done? What if done is false? Then we don't call ck exit. What happens to the object? What is it running? Nothing. It just sits there waiting for someone to invoke a method on it. So this is the common fate of most Charm++ objects. They just sit there waiting for something to happen to them, right? Someone will invoke a method, then they will run it, and so in that sense they are said to be reactive, all right? They react to someone sending a method invocation to them, and when they finish running the method, their memory, everything just stays intact. They just go back and they just return, and the object just sits there. All right. Okay. This slide is titled, "Does this program execute correctly?" So now I have a first question for you. How many of you think it executes correctly? You're all smart people. This is cannot be, the answer cannot be yes, it runs correctly if I put that on that slide, right? Okay. So what's the problem? All of you. How many of you think it does not run correctly? It's always useful to ask that. Aha, I see. Half of the class has not made up their mind yet. Okay. Someone tell me, why does it not work correctly? Raise your hand. Yes, Jamin. Yeah, we might send one, we might, what we are sending is calls with 1, 2, 3, 4, 5 for the first parameter up to 9 with false. And so 1 false, 2 false, 3 false, and so on are the messages that are going towards it. And 10 true is also going towards it. Who knows what order they will reach that processor? Who knows what order they will be executed in the queue in that processor? And so it is possible that it will execute 1, then 3, then 2, then 7, then 10. And then it is planning toward the other messages sitting in the queue for the rest of the things. But as soon as it executes 10, it calls CK exit, the whole program terminates, and you didn't see the answers for all the radii that you sent, right? You see that bug? Okay, now the question is, how do you fix this bug? Yes? Always, when I ask a question, answer it based on what has been taught in the class so far. If you have read the manual ahead, or if you know something because you are from my group, don't use that knowledge. Okay, so yes, Monica. But the find area's functionality, we want to keep it very simple. It shouldn't know the logic of the main char, what it's trying to do, right? We want to give the control to it somehow. So otherwise you can say find area can chain itself. The next one, say, hey, you printed the area of a circle of radius 3. Now make sure you call 4. So it will call recursively itself. That's your solution. Okay, that's doable. Something else? Yes. Main char keeps track of which ones have been printed.
Yeah.
How can it do that?
For example, if a char has done its job, it can send back an acknowledgement or something.
Aha. So it can. You want the simple char to send back an acknowledgement to the main char. How will it send the acknowledgement? It has to be another method. So I must have in the main char another method that says act, right? And so, and then when it gets, so then what should it do? Yeah, but then we don't need this parameter, isn't it? We will always say, hey, find area for I and let me know when you're done, right? And so we don't need the false or true parameter when all of them, and you don't even need two separate loops, I mean two separate calls. You can say for I going from 1 to I less than 11, find area I, no second parameter needed, and you have another method here says that says ack, and ack will simply count up and say how many acks have I gotten. Right? You don't have to know, the acts might come in different orders too, but you don't care. You just need 10 acts. When you get 10 acts, then you can say, okay, I'm done, call CK exit. That's another solution. Any other solutions? Which is what she's doing, by the way. Right? CK exit after the act. So you cannot put CK exit right here. What will happen if you say for I going from 1, I less than 11, sim.find area, you don't need the second parameter, and just put CK exit here. It will exit before those calls are processed on the other side, right? So remember, this is asynchronous method invocation. Those invocations are on their way somewhere, right, in the ether. Just think about when you send a method invocation, it's just sitting somewhere. You want to debug your program, imagine things getting delayed hugely. Then you might find a scenario in which the bug that you're seeing manifests. right? Okay, so those are some ideas. You can do either one of those is fine, and you will find probably some other ways of doing it. Okay, we're going to look at some one other program and introduce a couple of constructs through that program. I have to apologize when I introduce this program always. There are much better ways of finding Fibonacci numbers and much better ways of parallelizing it. Fibonacci numbers, you all know, Fibonacci of n is Fibonacci of n minus 1 plus Fibonacci of n minus 2 unless n is less than 2, in which case Fibonacci of n is n. Fibonacci of 0 is 0, Fibonacci of 1 is 1. And so this leads to a naturally doubly recursive program, which is very natural. If n is less than 2, return 1, return n, otherwise return fib of n minus 1 plus fib of n minus 2. How to do this in parallel is what we are going to look at. But first of all, you all know a better way of doing that, right? This way will be, in terms of n, how long would it take? Recursively, forget the parallel program. Asymptotically, can you say how long does it take? Order n log n, what is it? It's exponential, right? The depth of the tree is n every time it goes down by 1 or 2, and the branching factor is 2, and so it's going to be exponential, 2 to the power n or 2 to the power n by 2, and it's going to be a sloping tree like that. So it's exponential, this horrible complexity. Can you do, how much faster can you do it? Linear? N is 0, n is 1, so that's true. N of 2 is, just use the previous 2 and add them up. 3, you just memoize this function, right? So-called memoization is the idea that if a function is maybe called repeatedly, then might as well store the result of the function in a table if the table is not too big. And so we say, I want to calculate Fibonacci of 25, that's Fibonacci of 23 plus Fibonacci of 24 plus 23. In the process of calculating 24, you will come to 23 again anyways. At that point, you will stick it in a table, and then when you come to the right branch and say, what's 23? You will just first always check the table, right? And of course, if you do that, you will have a table of size n, and your program will still run in size n, because every time you actually need to calculate a value, that will be only once. Other times you'll just find it in the table. So you're going to find every value, calculate everything once by just adding the other 2, and at other times just find it in the table. So it will be order n. And you can eliminate the table by noticing, you just need the last 2. You can build them up bottom up, 0, 1, then 2, then 3, then 4, then 7 is just 6 plus 1, 6 plus 5, Fibonacci of 6 plus Fibonacci of 5. So you can just, don't need the table, you just have to keep track of the last 3 values, 2 values, and calculate the third. All right, that sounds pretty fast, and we're doing exponential. But Monica, did you say logarithmic? Oh, you didn't. Anyone thinks you can improve on that linear? In fact, you can improve on that linear. In fact, you can do it in logarithmic time. So instead of logarithmic, we can go linear. That will be one level of badness. And from linear, we are going to go exponential. That's another level of badness. And we're going to do a yet third level of badness, which we will fix by the time we get to the end of it, which is not doing the grain size control. All right, let's see. But Fibonacci is a great example for illustrating divide and conquer parallelism. And divide and conquer parallelism is not something that people use a lot in science and engineering. Maybe there is some Strasson's matrix multiplication or adaptive quadrature, some things like that that occur in HPC that are useful there, that use divide and conquer. But mostly we do iterative calculations with data. But I think it's good to illustrate with Fibonacci the divide and conquer idea, and then we'll move on to next lecture. We'll move on to the more iterative types. So when we create a char of type Fibonacci or fib here, char class fib, it has a constructor which is given a number n, which is the number nth Fibonacci number that it's supposed to calculate. But in addition, it is given some additional parameters, because after all, it has to return the value to its parent. We are going to recursively generate them, right? A char will be created for calculating Fibonacci of 29, which will create two chars for creating fib of 28 and 27. And that 27 will create two for 26 and 25. That those two, when they finally find the value, will send it to the parent, which is the Fibonacci, calculating Fibonacci of 20, what was it, 23, where did I mess up? Anyways, 23, whatever that was, and it will send, so the values are going to come up the tree. You need to know who your parent char is. So that's going to be a proxy of type fib. So C proxy underscore fib parent. That's going to be one parameter. And then when it comes all the way to the first guy created by the main char, say, hey, calculate the Fibonacci of 28. Well, that char is at the root and everyone else is not at the root. That guy's responsibility to print the result. So we're going to pass a parameter called isRoot that says, hey, if you find a solution, just print it and call ckexit. All right. And so since you're going to need to send something to your parent, it needs to have a method like the ACK method you came up with earlier. Let's call that method respond method. There's always a little bit of an ambiguity when you write charm programs, whether to name the methods from the point of view of the sender or from the point of view of the char itself. You know, so in fact this one is probably a pretty bad name. But if you say a response, then that's nice name from the parent's point of view. But child is saying parent.response. Well, if you're used to C++, you know, invoke the response method on the parent. But if you, but in some other cases, some other verbs might make more sense to you. But naming it from the parent's point of view is usually a good idea, from the receiver's point of view. So here, let's say we called it respond. Probably not a good choice of name, and it's simply the value Fibonacci. Whatever you ask me to calculate Fibonacci of, the value is this, is what you're telling the parent, right? So like I said, .ci file should make a lot of things clear about what your intentions are. Let's look at the code itself. Can you see it in the back? My guess is not very clearly. Let me see if I have lights at least under my control. I was pretty sure I have a light here. Okay, well, but basically the main char simply does nothing but create the fib char instance, C proxy underscore fib, and provides to it the argument provided from argv1, and then second parameter is true, you are the root, and then provides to it something. It doesn't have to, it can, it's saying C proxy underscore fib open close. This is just a way of passing a null pointer of type that, right? Because you're not expecting anything back from that guy. That's the root, is going to print the result. So you just want to basically pass a null there. So what does the every fib char do? This is the usual C++ way of storing it. So it gets a parameter called parent. It stores in the variable called parent. IsRoot underscore is stored in isRoot. It gets it initializes the variable result and count. If you're not used to C++ that much, that's how you initialize variables. You could have said result equals 0, count equals 2. It's the equivalent. And so then the code is simply, if n is less than 2, then call the respond method, which in this case will, call the respond method. Otherwise, create two chars with n-1 and n-2 with again false, because obviously if I'm creating chars, then I'm not, then they are not the root. And so false, and you provide to them your proxy. So this proxy, analogous to this, is a globally valid reference to me. And so you pass that reference as third parameter here. When someone calls respond, either because their children call respond or because they themselves were tiny enough, then you say, well, maybe I just got a response from my child. So you're going to count those, how many responses you have got, you're going to count them down to 0. So you either you pre-decrement the count and see if it reached 0. That means you got both the responses from the two children you created. Or n is less than 2, in which case you didn't create actually any children, but you are done. You are a leaf. And so in either one of those cases, you need to either print the result or send it to your parent. So if I'm in the root, then I print the result, call ck exit. Otherwise, I call my parent parent's respond method, and with the result that I calculated. Where is the result? Well, that just anytime a child comes and gives you a value, you add it to the result, which is initialized to 0. So when the two children give you the value, they become that becomes the right value to return to your parent. And then we have this abominable thing, delete this. You normally don't want to do that in C++, but in Cham++, who is going to delete this object? There is no one else to delete this object, so you just say, so it's allowed to say delete this for a char object. Okay. Notice that the respond method is being used in two different ways. One as just a local call here, and the other as an asynchronous method invocation in another proxy, via a proxy to the parent object here. And that's okay. Entry methods can be directly invoked like this. Respond is an entry method, but it can just be invoked like any private or public method locally. Does that make sense, this code? Now, compared with a simple divide and conquer language, this is pretty ugly, but this is a function of how a library-based language deals with things. And later on, we'll try to figure out ways of improving on the syntax for it. But that's not the point right now. The point is to learn this in this most general form, which is what you're learning right now, method invocations, char creation, right? Does that make sense? Okay. What are the things in this program that you would like to improve, even based on what you already know? Or maybe just trying to wish for some constructs, either way. What things aesthetically bother you that you would like to fix? This works correctly, no problem there, right? A char will create two children, which will create two children, and so on. When something is a leaf, it will just call the respond method, which will send it to the parent, and the process will go recursively, and the first char created by the main will print and exit. All works correctly. Performance-wise, aesthetics-wise, any issues? Yes?
Seems to be creating a lot of objects, and each one does very little work, so there's a lot of overhead.
We saw last time that the grain size issue is important, that you want to do work large enough for each message to amortize the overhead of asynchronous method invocation, which I said could be like a microsecond. Imagine it to be a microsecond. So on the average, you want method invocations to be tenths of microseconds. This clearly is not. The respond method is just adding, well, it has a couple of if statements and one addition if you are doing that addition, and then just deciding whether to send the result to the parent. This constructor just creates two objects. Those are going to be nanoseconds, tens of nanoseconds, hundreds of nanoseconds effort. All right, one problem. Let's come back later and solve it. What else? Is it bothersome that is root business? What would you like to do instead? It would be nice to not have to say, am I the root? Depends on if the main char gets a response back, it can say, oh, I'm the main char, I will print it. So maybe the responses can go to a respond method in the main as well as a respond method in the fib char. That turns out to be more challenging for various reasons, but that's another thing that you could maybe fix, and that could motivate some constructs in the future. The fact that the logic is spread out, you create this object, you create the children, and then as a response comes you do this, as another response comes you do that. It's very reactive logic, and that detracts from the expressiveness. All of these issues we'll look at remedies for later on, but for the purpose of the constructs we are learning, they are absolutely fine, and they are complete by themselves, and you can actually write programs using it. Grain size, though, can be fixed. We basically want to say, we want to put a sequential threshold. You say, well, if n is less than 10, just calculate it sequentially. 10 sounds like a big thing for an exponential function, but even exponentially 2 to the power 10 is only 1,000. And so you might want to raise that actually by doing some experiment to see how long it takes. Of course, if you're doing that experiment, you realize, oh, you should be using a simpler method, but forget that. You could examine a particular value. You can set a particular value for threshold and say if it is less than that threshold, just do it sequentially, which now puts the onus on you to write the sequential code, again exponential because you don't want to change the algorithm, recursive sequential code for calculating Fibonacci of n inside the object. So you'll say if n is less than 2, instead of that you'll say if n is less than 10, then call my sequential recursive function. Otherwise, fire the 2 children and do the work as usual, right? If n is less than 10, call my sequential function, get the return value, and call respond with it to complete that train of thought. Yes, you can do that. But now to express that 10, and you want to change that 10 sometimes, you will just go and edit the program and find where that 10 is and change it to 12 or something, 11, whatever you want to experiment with. But there is another construct that's useful here. Read-only variables. In Cham++ programs, you are not allowed to have any global variables except read-only variables, right? And the reason for that is simple if you understand the implementation. There are many, many nodes. The Cham program is running on a large collection of nodes, 10,000 nodes on Blue Waters, each one running with 20 cores. If you have a global variable, that global variable is a simple compiler, library-based language. It's going to be an instance on each processor. And so if you modify it, then others are not going to see that modification, unless that modification means edited everywhere, and then you have to deal with all kinds of race condition issues. So the Cham++ semantics is simple. It says the only global variables allowed are read-only variables, and so the question becomes, how do you declare them, and where are they? Well, of course, a read-only variable is still a variable, which means you get to assign its value. It's not a constant. And the reason is because at the beginning of the program, somewhere, you might have to do some calculation to decide the value of this variable. So in constructor of a main char is the only place you are allowed to assign a value to a read-only variable. After that, the system will make sure from every char, when you ask what is the value of this variable, you will get the same answer, irrespective of which processor that char is running on. And you are just honor bound not to modify that variable. System will not detect that, but you should not be modifying a read-only variable in the program, right? Okay. So how do you declare it? Well, in the .ci file, you just say read-only int grain size. Whatever variable you chose to do, here it's a grain size. And in C, you just declare it like a normal global variable. So here, our Fibonacci example, same, everything else is same. I just added this one extra line, read-only int grain size. And in the .ci file at the top, I said int grain size. It's a common convention to put in comments to the left of that, slash star read-only star slash, so that you remind yourself it's a read-only variable. Okay, but if I put it there, you might think it's a requirement. So I omitted that from my example. And then here, on any arbitrary char running on some arbitrary processor, you can say if n is less than the grain size, respond. Now, of course, I didn't put the sequential fib here. Respond sequential fib n is what. So there's a bug here. This n should be respond with sequential fib, letting sequential fib calculate the value and send it there. And so result is value. Well, you might have to say val equals sequential fib and then respond. That might be the right thing to do. So there's a bug here that you can fix, but the basic idea is clear of how to use the grain size, right? Well, let me give you one more example and then ask for questions. Let's say we want the main char to print the result instead of the char created by the main char in that same Fibonacci. So how do you modify the program to make this happen? Of course, you can have the main char have another entry method for receiving the results. You need to have that, right? The main char has to have a method which will be called, and then it will print the result. And then the root, the code inside the isRoot branch goes inside that, right? Basically, ckprint and ckexit will all go there. And so, but in the fib itself, what should we do when you are in this branch? We know we're not going to be doing the printing, but if I'm the root, then I'm going to tell the main char to print it. So I want to say, what is the proxy for the main char? Respond, whatever the name of the method I choose, or done, and provide the value. So here I will simply say main proxy dot respond with result and no ckexit, because it's going to call the ckexit, right? So so this simply is, can't. So then why are you sitting there? Okay. Anyway, so that's what I would change here. I would just say main dot done result, and then that one will print it and call ckexit. The question is, what is this main? I need to have a proxy for the main object. How do I get a proxy for the main object? Maybe the fib constructor should be given the proxy for the main, but then when it recursively creates its children, they don't need it. Or maybe I need to create two different types of fib chars. One that are called from the root and one from not the root, because the constructor for one of them will have the additional parameter. But you can do something simpler than that. You can just put the proxy to the main object in a read-only variable, right? So so what you do is store the main char's proxy in a read-only variable. All that. How do you do that? When you are in the main char in the constructor, you say this proxy, and assign this proxy to a variable called main proxy, and declare main proxy to be read-only in your .ci file. So in the .ci file says read-only main proxy. Does that make sense? No. Read-only. What am I missing? Remember, read-only int grain size. Read-only cproxy underscore main, that's the type of it, main proxy, semicolon, right? So read-only is a keyword, type of that object, which is cproxy underscore main, and the variable name, which we chose to be main proxy. And then in the main char, you will say main proxy equals this proxy, so that this proxy, this object's proxy gets, global reference gets stored into this variable. And the system will make sure it's available on all the processors. So wherever that first char is created, it will send a method invocation to the main proxy. Okay. So in Fibonacci example, you will just do cproxy underscore main proxy equals this proxy. Here you added read only. That uppercase should be lowercase. Cproxy underscore main proxy, and so here you simply, I don't think I modified this. This one here should be then modified. If I'm the root, then main proxy dot respond and modify the rest of the program accordingly. So I was just sketching a solution here. You can then complete that solution. Yes?
So I have two questions about the previous code.
Yeah.
First one was...
This is my last slide. Yeah, okay. Go ahead.
There was like, in that CKMU, you said cproxy underscore fib.
Yeah.
That's supposed to be null? Or
That's basically a way of constructing a null of the right type. Right? It's basically just a null. If you pass null, it should still work.
And then my other question was, is there like the concept of interface proxies? So like interfaces are virtual methods?
You can define virtual methods. You can do inheritance in chars, and so that works like in C++. If you go very deep with complicated things, you might encounter some translator trouble, but those will be bugs of some sort, yes. But yeah. Any other questions there? Yes?
If you have main proxy as a global value,
You still need what?
the value.
Do you need isRoot? How are you going to find out that you you are the one who needs to send it to the main char.
You can check whether this proxy equals
But no, because main doesn't know about any logic of Fibonacci, right? So the Fibonacci logic is all inside the fib. The root of that tree, which is a fib char, is the one that's going to send the result to the main. Therefore, right? But there is something to what you're saying, but we won't get there until like 4 lectures later. You would want to eliminate ease root somehow. Much later we'll see how we can do that. Okay. So I just want to get. I know we're late. I want to get one quick concept done, and then we can stop here. If you want to pass, so far I just said int or double, but you can send arrays too. When you send arrays in the .ci file, you have to say int data and give a size parameter, right? This size expression can include some other things in your parameter list. So in this case, it's length, or it could include read-only variables. Or some function of those. Like you could say int data length square, right? Length star length. Or you can say int data length star x, where x is a read-only int, right? And so any expression is okay, but you have to have an expression. In the C++ file, of course, it's just going to be a pointer. So, and so you would have allocated it of the right size. The system is going to just follow the pointer, take that many ints from there, and then package them into the message. So that's one thing that you have to understand about sending array parameters. Ignore this comment for right now. You can, so far all that you know is the base types, int, float, char, etc., and then their arrays is all that you can send as parameters. Later on we'll see that there are you can send arbitrary parameters with all kinds of types, but we'll need to learn some new constructs for that. Okay, and as an exercise for putting everything together that we have learned, you can write a very simple, no complicated heuristics n queens program, and think about based on the heuristic on this slide, based on the idea on this slide. All right, let's stop here. Any other questions? Okay.